Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 3 of module 9. In the current module, we are covering the topics such as the earthquakes, focal mechanisms, moment tensors. In the lecture today, we are going to talk about moment tensor, and then we will discuss about equivalent forces. Specifically, we will take on to the single forces, force couple and double couples. And finally, we will be having the summary of today's lecture. In the recap, for the previous lecture, we learnt that the seismogram recorded at various distances and the azimuth can be used to find the fault geometry during an earthquake, that is known as focal mechanism. And it uses the fact that the pattern of radiated seismic waves depend on fault geometry. That means the different fault geometry have different patterns of radiated seismic energy in the form of seismic waves. In the previous lecture, we also learnt about the first motions, where we saw that the zone of deformation can be divided into 4 quadrants, 2 for the compressional and 2 for the dilatation, and these quadrants are separated by nodal planes known as actual fault plane and the auxiliary plane. And it is sometimes hard to find out the actual fault plane and the auxiliary plane until we have the expression of the fault coming to the surface. For this purpose, we need additional information that may come from the geodetic data, or maybe you have the other information from the geology, or maybe from the pattern of the aftershocks you can identify the actual fault plane. Fault plane will be the auxiliary plane. The elastic radiation can be described as resulting from the double couple of forces. These forces are known as equivalent body forces for the fault slip. In the previous class, we also saw that if this is your fault plane and this is your auxiliary plane, then along the fault plane, let's suppose the slip is happening in this direction for a left lateral strike slip fault. So in this case, it will generate the compression over here, and in this case here it will be the dilatation, and it will be the compression. And same deformation may also be produced by a force couple that is acting on the auxiliary plane, and that can be something like this. So in case you do not have any information about the fault, then you may not be able to identify from the first motion that which plane is the fault plane and which one is the auxiliary plane. So for this purpose, as I said, you need additional information. So those information may be coming from the pattern of the aftershocks, maybe from the geology, or may also come from the geodetic data. So in case of compression, the first motion will be having the first motion in the upward direction like this. And in case of dilatation, the first motion may be having the negative polarity. So this is the positive polarity in case of compression, and for negative polarity, it will represent the dilatation. The radiation pattern for P wave and S wave can be given by using these expressions for the displacement, and the displacement along the radial direction can be represented by 1 by 4 pi rho alpha cube r m dot t minus r by alpha sine 2 theta and cos phi, and this is the seismic moment rate function. and this is the amplitude, and this will represent the radiation pattern of the P wave. So if you look at the first term, then it is having the density term, velocity term alpha, and also having the distance term r. So you can say the amplitude of the P wave energy is inversely proportional to the distance. That means the seismic P wave energy will be attenuated as a inverse function of r. Similarly, for the S wave, the displacement term will be depend upon the theta and the phi in the spherical coordinates, and for u theta it can be denoted by this expression, and for phi it can be denoted by this expression, where beta is the shear wave velocity and this is the seismic moment rate function, and this will represent the radiation pattern of the S wave. If we start with the today's lecture, let's start with the Green's function, which basically is the path effect in case of an earthquake. When the earthquake energy is radiated by the source, then the radiated energy will get convolved with the path, and then finally it will reach to the location where we are going to make the observation. If suppose we want to discuss about the Green's function and its association with the body forces, first let's recall the moment equation consisting of body forces. The moment equation that consists of body forces can be written something like this: rho del square u by del t square is equal to del sigma ij plus fi, where sigma is the stress and f is the body force. In the previous lectures, we have been ignoring the body force term, but these will be considered now because earthquakes are a body forces. The simplest body wave force or the body force can be represented by delta function, and it will have the direction f, that is a vector quantity, and it will also have a location x0 and t0. x0 is again a vector quantity, t0 is not a vector quantity. The displacement uxt of Earth due to this force at location and time x, t will be given by this particular expression. Uxt is the displacement at a location on the Earth, x at a time t, and g representing the Green's function, f is the body force. So the body force, when have the effect convolved with the path effect, then it is giving the displacement. The path effect is being represented by this Green's function g, and in summation notation, at a particular place when many of the body forces are acting as a source, then for different sources we have several path effects, and those will be summed up together to give the net displacement at a location. In the summation notation, the displacement or the net displacement ui can be given by gij product with fj, that is the body force term. Now let's talk about moment tensors. Moment tensors or the seismic moment tensor comes into picture when we generalize to include all type of seismic sources. Seismic moment tensor can give the additional information or maybe the complementary information and can provide the insight into the rupture process and can greatly simplify inverting seismograms to estimate source parameters. So seismic sources, let's suppose explosion, landslide or impact on the earth's surface, all these sources may generate the seismic waves, or you can say you can observe those seismic waves, and these seismic waves can be used to find out the seismic moment tensor by assuming the equivalent body forces, and these moment tensor can give you the idea of source parameter. That is basically our aim to find out the fault geometry. Since now we are talking about the body forces, let's talk about the force couple. And the force couple, as the name it suggests, consists of two forces that acts together, and it has two basic force couple types, and this is a example of single couple. Here two forces are acting. In this case, the forces are d distance apart along the y direction, and the force itself is acting in the x direction. So this is your x direction, and this is your y direction, and this is your x direction. So along the x direction, if the forces are acting linearly and at a distance d apart on the same x-axis, then it can be represented by mxx, and this is the off diagonal movement, that is mxy. So mxy is basically the couple, consists of two forces of magnitude f separated by a distance d along y-axis that act in opposite direction plus minus x directions. The magnitude of mxy is fd, which in seismology is given by Dye in centimeter or Newton meter. To model a couple acting at a point, the limit is taken as d goes to 0. That means in case the couple is acting at a point, you can keep d as 0 such that the product fd stays constant. mxx, the other type of couple, is a vector couple consisting of the forces offset in the direction of the force. mxx consists of two forces of magnitude f acting in plus minus x direction separated by d along the x-axis, and the magnitude is fd. If suppose there are the forces which are acting on a irregular shaped body, then we can have the moment as an integral or the summation for the entire area A. That will be the shear modulus having the product of d, that is the slip, and the elemental area dA. So on the elemental area dA, whatever the slip is, that is basically represented by this particular expression. And if we have the equivalent body of rectangular shape, then it can be represented by the area WL having the width W and the length capital L, and there will be a slip on the fault plane capital D equivalent to this irregular shape fault plane. And approximately we can write the force couple as something like this, or this is the double couple where there is this couple, one couple is there, and there is another couple like this, and these couples are d distance apart from the single force couple, and this is your m is equal to fd. So the moment tensor is a simple mathematical representation that gives the seismic waves produced by a complex rupture involving displacement varying in space and time on a irregular fault. So what you have seen here, the irregular shape body that is acted upon by the several number of forces, and where the moment can be found out by taking the integral over the area mu d into dA, elemental area. It can be replaced with an equivalent body of rectangular shape. So that means we are doing the simple mathematical representation of the moment for a irregular shape fault, and that is the W, L is the dimension of this rectangle, and D is the equivalent slip along the fault surface, and the moment, scalar moment, will be equal to mu into D, and the area is LW. The moment tensor again have some equivalent forces, and those equivalent body forces produces the same radiation pattern as the slip fault for the earthquake and the other seismic sources. So when we are making some approximation, we are also having the equivalent body forces, the body forces that are equivalent to these forces, and these forces, the equivalent body forces, will also produce the same radiation pattern as these kind of forces that are acting upon the irregular shaped body, and this radiation pattern, which is similar to the slip onto the fault for the earthquake and the other seismic sources. The seismic sources can be modeled as single force, single couple, and the force couple. We will see the details of these in the coming slides, but just to have a glimpse of it, since we are discussing these here, the single force is just a single force, if the x direction is in this direction and the y direction is in direction. So let's suppose this is the example of a single force, and this single force if has the two component, that means one that means in positive x direction, another is in negative x direction, then it may be referred as the single couple, and these are distance away d along the y axis, and this will be known as mx by or m in subscript xy. Or the single couple can be represented by this force where the distance is in the same direction along the x direction and forces are acting in the plus x and the y minus x direction, and this will be known as m in subscript xx. Let's take an example of fault for the double couple. On the other hand, the double couple will be represented by the two single couple, or you can say a couple of two single forces and another couple of two single forces. And this is the fault which is a left lateral strike slip fault. And why I am saying it is a left lateral strike slip fault, we have discussed about it into our previous lectures. And for this purpose, you can just imagine yourself sitting on this side and look at the motion of the block onto the other side of the fault. If it is going in the left direction in relative to you, then it is your left lateral strike slip fault. And this left lateral strike slip fault can be represented by this double couple, and these double couple are maybe d distance apart from each other. And in case we want to represent it in the terms of pressure and the tension axis, it can be represented by this, such that off diagonal element will become almost zero, and then in that case it can be represented by this, where tension is represented as a positive movement and pressure is represented as a negative movement. So you can see this is a negative and this is your positive. And since we want to understand the single forces, so single forces can be, let's talk about these seismic sources which are single force, single couple and a double couple in detail. So let's first take on to the single force, and geophysical phenomena can be used to generate the seismic forces that are sometimes modeled as single force sources, and it can be from the volcanic eruptions, landslides and the meteoritic impacts. And this is the modeling of 1980 Mount St. Helens eruption as a single horizontal force. So this is the single horizontal force Fx acting on to the x direction, and here you can see the amplitude in centimeter seconds, and here you can see the love wave. This is for the love wave and this is for the Rayleigh wave, and here is the horizontal force and this is the vertical force into the screen, and this is for the isotropic source. And for the horizontal force, this is the picture that is for the amplitude radiation pattern. Likewise, this is for the same, and this is also for the isotropic source. And in case of double couple, if we are talking about the left lateral strike slip fault like this one, that is having the slip in plus minus y directions on a fault in yz plane, the equivalent forces can be mxy plus myx, that will make up the double couple, and the myx will be having the complementary component, that is mxy, that will basically be needed to have the no net torque on the fault. So this is what it is written. The myx couple seems intuitive because the force point in the slip directions, but the mxy couple is also needed for the reasons including avoiding net torque on the fault. So the relation between an earthquake fault geometry and the double couple of the equivalent forces is given by these diagrams, and there you have this t axis, there is p axis, such that off diagonal element are small or zero, and the pressure axis is represented by negative movement, and the tension axis is represented by the positive movement. The slip on a fault can be represented as a series of the fault couple. This is the array of the moment, and it can be represented into the tensor form like this. And the moment tensor is similar to the stress and strain tensor. It has the on diagonal element or diagonal element and off diagonal elements as well, and the direction of each of the moment or the force couple can be seen like this, and this is for the x1 direction, this is for x2 direction, this is for x3 direction. Since we are having the conservation of momentum, each couple must be balanced. So if there is M12, then there will be M21 will be there to have the net torque 0. So this is your M12 and this is your M21. When we are using the moment tensor with the Green's function, we earlier saw that for a point force, the displacement can be represented by this expression where G is the Green's function, that is representing the path effect. F is the body force term. When these have the product of both of these together will represent the displacement at a point on the earth. And if there are number of forces acting, then in the summation form this can be summed up together, and the path effect will also be summed up together, and then we can have the product of both. Thus, the displacement at x due to a force couple at x0 can be written as something like this. Since you can look at this diagram, here a force is acting in this direction, and after a displacement of dxk cap, then there is another force that is acting in positive x direction, or you can say the opposite direction. So the net displacement can be written by this expression. The negative term is for the direction for the force that is having the opposite direction to this force, and there is this term that is basically the displacement, and you can see there is a force term, body force term as well. You can rewrite this in this form by multiplying the d parameter onto the numerator and the denominator both. Then this will be looking like as a derivative, and in the derivative form it will be something like this. So it basically shows the displacement in I direction for a force couple in the j direction separated by a distance d in the k direction. Since we are talking about the force and the sources, and we have talked about the single forces double couple, for the double couple itself we can represent the magnitude of the equivalent body force as m0. This is your scalar seismic moment of the earthquake, which has unit 9 cm similar to those of the force couple. The mxy and myx are couples of unit magnitude. The moment tensor can be represented by this. The moment tensor has components that signifies the fault geometry, and it also has the scalar component that signifies the size of the earthquake. The displacement due to the double couple can be written in this form, as we have seen from our previous expression. The displacement can be written in the derivative form like this for the Green's function, and here this particular expression is mjk, that is moment, or you can say it is the force in the jth direction offset by d in the kth direction. So this basically representing the force and this representing the offset direction. So where j is the dummy index and can be expanded in this form, you can see that this is the third column of the moment matrix, that is this one. This is the third column, this one. So these are the direction in x3, and this is your f1d, this is your f2d, and this is your f3d. So this picture is taken from the direct shoot, a professor in the Colorado State University. Now understand how can we relate the moment tensor to the actual geometry of a fault. Let's suppose if you have this fault, where we have the slip along the x1 direction, and if it is a right lateral strike slip fault, then it will have this double couple M21 and M12. And in the moment tensor, it can be represented by this, where you have M212 and M21. Since the other couples are 0, so other couples have been kept 0. And M12 and M21 can be written as M0, and this M0 is equal to mu D into A, where D is the slip, A is the area, mu is the shear modulus, and this M0 has the unit of the work. So the M12 and M21 can be replaced with M0. The moment tensor, similar to the stress and strain, are symmetric in nature. There will be a set of axes which will make off diagonal element to 0. The off diagonal elements will become 0 at 45-degree rotation. So this is for the 45-degree rotation, P and T axis. And in the new coordinate system, we can replace M11 as M0, M22 as minus M0. So this will become M0 and this will be minus M0. For the tension axis or for the stretching, the moment will be positive. So this is for the tension. And for the pressure axis, the moment will be negative. So this is for the negative, or you can say the pressure. The M0 can be written as this, that is 1 by 2 summation ij m ij square to the power 1 by 2. The positive moment implies stretching or tension, while negative moment implies pressure. In summary, we can say the seismic moment tensor gives additional insight into the rupture process and greatly simplifies inverting seismograms to estimate source parameters. We assume the equivalent body forces which produces same radiation pattern as the slip on the fault for the earthquake and the other seismic sources. The seismic sources can be modeled as single forces, force couples and a double couple. The component of the moment tensor represent the fault geometry and size of earthquakes represented by scalar moment. Moment tensor is symmetric in nature, just like as that of the stress and strain. There will be a set of axes which will make off diagonal elements 0. It is similar to stress and strain tensor. These are the references. Thank you so much. Bye-bye.